Alright, welcome back. In this video I just want to go over quickly how current division works and what the formulas are for it. So this is when we have a simple parallel circuit or just a bunch of parallel resistors connected to a power source. And you might be familiar with these expressions here where we have the total resistance in a circuit like this is just equal to 1 over, and then we sum the inverses of each of the resistors. And you might also see this expression here where the current through any particular resistor is equal to the total current of the circuit times the total resistance divided by the resistance of that individual circuit that we're considering the current to be flowing through. So if we were just looking for these expressions, here they are. But if you have a few minutes and you're here already, then we can just quickly talk through how we actually get these, which I think is a useful thing to know. So looking at the circuit here, when we talk about I total, that's this value here. That's the total amount of current flowing out of the voltage source, and it's also the total amount that's flowing back in. When it gets to this junction here, what flows in has to flow out, and the current that's coming down is what we're going to call I1. Same thing here, the amount that flowed out of the previous junction has to come here and then has to be split again, and the amount that comes down here we'll just call it I2, and the amount that comes through this branch we'll call I3. Now you might remember from previous videos that in a circuit like this we say that the total current is just equal to the sum of all of the currents in the different branches. And we could obviously just rewrite that in this case where we have I tot is equal to I1 plus I2 plus I3. Now when we look at this expression for total resistance, this is actually being basically derived from our conductance expression, and conductance has a very similar format. We say that conductance, which is the capital letter G, so we'll say the total conductance is just equal to the sum of all of the individual conductances. And for a system like this with just 3 resistors, we would say that the total conductance, G tot, is just equal to the conductance of resistor 1 plus the conductance of resistor 2 plus the conductance of resistor 3. Now just to recap, conductance is a measure of how easily current can flow through something, and it's basically just the reciprocal of resistance. So we use the capital letter G, it's just equal to 1 over R for resistance, and that means that resistance is just equal to 1 over G. They're reciprocals of each other. If you want a recap of a little bit more information about conductance, then I'll put a link to a video in the top right corner that basically goes over the introduction to what conductance is. But basically, when we have a parallel circuit like this with many resistors in parallel, when we add more branches, we basically increase the conductance because we just keep adding values here. And by doing that, we actually decrease the resistance, and that's ultimately because there's more paths for the current to pass through. But what we want to do is we want to go from this expression for total conductance to this expression for total resistance. Now, how we can do that, first of all, is by taking the inverse of both sides. So let's inverse the left-hand side, and then we'll take the inverse of the whole right-hand side as well. All this means is we just divide both sides by 1, so we have 1 over G tot is equal to 1 over this summation. So this was G1 plus G2 plus G3. Now 1 over conductance is just equal to resistance. And we have the subscript of total there, so the total 1 over the total conductance is equal to the total resistance. So we can write that for the left-hand side. That's R tot. And then we have the right-hand side, which is 1 over. And when we look at the first thing here, it's G1. Well, G1 is equal to 1 over R1. So we can write that 1 over R1. G2 is also just equal to G2 is equal to 1 over R2. So we have 1 over R2, and G3 is 1 over R3. And when we look at this, this is the exact expression that we had over here. R total is equal to 1 over the sum of 1 over each of the individual resistances. So that's exactly how you derive this equation, which gives us basically the equivalent resistance of the circuit from basically the perspective of the battery. So instead of having these 3 resistors, we could basically cut these and remove the right-hand side of the circuit and then just connect one equivalent resistor here. And as long as that has this value, this resistance, then the voltage source really could care less if it's one single equivalent resistor or the 3 actual parallel resistors. Okay, so now that we know the total resistance or the equivalent resistance of the circuit, then let's go ahead and figure out the current divider formula. So let's take Ohm's law first, which is V equals I R. Let's give subscripts here. So actually it is total, the total current, and then the total resistance. And that's going to give us the total voltage drop, basically from this node at the top to this node at the bottom. So if we rearrange this, we have I total, the total current is just equal to the voltage drop over R total. And just to be clear, that is, when we talk about the nodes, let's shade on this top node here, and then let's shade on another node down here. So the voltage drop is going from the red node to the blue node, because if we were to disconnect all of these three and replace it with an equivalent resistor, it would also go from the red node to the blue node. But we can also rewrite Ohm's law with an expression basically just going through one of the actual resistors. So we can just write that just like this, with current through any specific resistor is equal to the voltage drop across that resistor divided by the individual resistance. But notice that the voltage drop across any given resistor is always going from the red node to the blue node. So it's actually going to be the same. This V here is equal to this V. So what we can do, we can replace this V, which is right here, it's equal to I tot times R tot, and substitute it in to this guy. And then we're going to get this expression that is individual current flowing through one of the resistors is equal to I total times R total over Ri, the individual resistance. And then you can really see that if you just bring this I tot out, then you have this expression here. So the individual current flowing through one resistor is equal to the total current times this ratio of total resistance over the resistance of the individual resistor. So yeah, if you're asked to derive the current divider formula, that's how you do it. And this is the current divider formula. If you're asked to derive the formula for total resistance, you can do it from the total conductance formula. But either way, I hope this video helps, and I'll see you guys in the next video where I'll go over an example of a current division problem with parallel resistors.